So you already on?
Sorry?
Oh, just checking if you were already. Oh, right. I was confused by the fact that one of you is muted, and I saw the mute thing. Didn't realize the other of you is not muted. Okay, very good.
But I think it's fine. I think exactly one of me should be unmuted, and that would be optimal.
No, it's perfect. It's perfect. It just created some cognitive dissonance because I saw you with the little mute thing. Your mouth was moving and words were coming out. How is it possible?
Right. Yeah. Yeah. I think the current setting's fine.
All right. So maybe it's a good time to get started. So welcome all once again to the Western Hemisphere Colloquium in Geometry and Physics. Before I introduce the speaker, I'll just quickly remind you about our ground rules. So the talk will be 1 hour long, and during that hour, if you have questions, you're encouraged to type those questions into the chat box. Just send them to everybody, and then I aggregate those questions and pass them on to the speaker as appropriate, or perhaps they'll be answered by other participants, which is a lovely bonus of these virtual seminars. And then at the end of the talk, there'll be a period for questions. And if you want to ask a question during that time, you just use the Zoom raise hand feature. We'll unmute you, and then you can just ask your question in the usual audio way. We're very glad today to have Lauren Williams from Harvard speaking on hypersimplex like the Amplituhedron. And take it away, Lauren.
So thank you very much for the invitation. If you want to download a copy of my slides, I posted them on my website. And the two main references that I'll be speaking on are joint with Tomek Lukowski and Matteo Parisi, and separately with David Speyer. So I'll start by just giving a sort of pictorial overview of the talk. So I'll first tell you about some beautiful old work of Gelfand-Goresky-MacPherson-Serganova on matroids and torus orbits on the Grassmannian. And then I want to tell you about a much newer object called the Amplituhedron, which was introduced by Arkani-Hamed and Trnka in the context of scattering amplitudes in n=4 super Yang mills. And the main purpose of my talk is to explain some connections between these two objects. And the way that we found the connection went through yet a different object called the positive tropical Grassmannian that David Speyer and I first studied back in 2005. Okay, so now let me give you a few more details on the program. So I'll tell you about the geometry of the Grassmannian and the moment map and this work of Gelfand-Goresky-MacPherson-Serganova. And here, key objects are the hypersimplex, more generally matroid polytopes, and the matroid stratification of the Grassmannian. And then I'm going to explain what happens if you add the word positivity to the previous picture. So this story with the adjective positive was initiated by Postnikov in 2006. And so I'll then tell you about the positroid stratification of the positive Grassmannian. And then we see objects like positroid polytopes and playback graphs in the picture, where playback graphs are also called by physicists on-shell diagrams. So then in work of Arkani-Hamed and Trnka from 2013, they gave a new definition, which is a simultaneous generalization of the positive Grassmannian and also polygons. And this object is called the Amplituhedron. And a main question about the Amplituhedron is understanding what they call triangulations of it. And I'll explain how triangulations of the Amplituhedron seem to be very closely connected to triangulations of the hypersimplex. And that connection goes, well, one way that we found the connection was via this positive tropical Grassmannian. Okay, so let me just give some notation terminology. So the Grassmannian of k-planes and n-space is just the k-dimensional subspaces of a n-dimensional vector space. And I will represent elements by full rank k by n matrices A. So here's a full rank 2 by 4 matrix. Its row span represents an element of GR24. And when we talk about the Grassmannian, it's convenient to talk about Plücker coordinates. So what's a Plücker coordinate? We'll give in an I, a k element subset of the numbers 1 through n. The Plücker coordinate P sub I of A is the minor of the k by k submatrix of A that uses column set I. So here, if A is this matrix, then for example, P sub 2, 4 of A is the determinant of the submatrix, which uses columns 2 and 4, which is 3. Now we have a torus action on the Grassmannian, which rescales columns of every element of the Grassmannian, and this gives rise to the moment map. So let me recall the definition of the moment map for the Grassmannian. So we'll let E1 through En be the standard basis of Rn. And now if I is a subset of the numbers 1 through n, we'll let E sub I just be the sum of the E sub lowercase i's for all lowercase I in capital I. So E sub I is a 0, 1 vector. And now the moment map from the Grassmannian into Rn is defined as follows. So in the numerator, we have this linear combination of 0, 1 vectors, E sub I. The coefficients are squares of Plücker coordinates. And at the bottom, we've divided by the sums of the squares of Plücker coordinates to make sure that everything, the images of all points, lie in the unit cube. So the moment map maps points in the Grassmannian into Rn. This is just a reminder of the notation. And then an old theorem, convexity theorem of Attia, Gilman, and Sternberg, which is true in much greater generality than just the Grassmannian, says that the moment map image of the torus, of the closure of the torus orbit on a point in the Grassmannian is a convex polytope. And specifically, that convex polytope can be written as the convex hull of the moment map images, mu of Q, where Q ranges over torus fixed points in this closure of the torus orbit. So, okay, so now what about the case of the Grassmannian? So I'll define delta Kn to be the convex hull of all 0, 1 vectors E sub I, where those 0, 1 vectors use precisely K1s. And so this is called the hypersimplex. The picture over here is a picture of delta 2, 4. And this hypersimplex is the moment map image of a generic point in the Grassmannian. So if you take a point in the Grassmannian where all Plücker coordinates are non-zero, and if you look at the torus orbit of this generic point and take the closure of that, then your moment map image of this closure of torus orbit gives you the hypersimplex. So this gives rise naturally to the notion of matroid. So the matroid associated to a point in the Grassmannian is a collection of k element subsets of 1 through n. And we're just going to make a list, make a set containing all k element subsets where the corresponding Pluker coordinate is non-zero. So this collection of k element subsets of 1 through n is the matroid associated to our point in the Grassmannian. And Gelfand-Goresky-MacPherson-Serganova showed that the polytope that you get by looking at the moment map image of this torus orbit equals the convex hull of the indicator vectors of the matroid associated to the Grassmannian point. And this polytope is called a matroid polytope. So it's a way of associating a polytope to a point in the Grassmannian. Okay, so this is, again, just a reminder of the terminology. And in their paper from '87, GGMS gave this beautiful characterization of matroid polytopes. And in particular, every edge of a matroid polytope is parallel to EI minus EJ for some I and J. Yeah, well, to just go say a little aside, this is a root direction. This is like a direction of a root for the root system AN. Anyway, that's an aside. But anyway, there's this characterization of matroid polytopes, and they always have this form. Your edge directions are parallel to EI minus EJ. And so once they had associated matroids and polytopes to each point in the Grassmannian, it was natural then to define this matroid stratification of the Grassmannian, where you partition the Grassmannian into subsets based on what's the associated matroid or what's the associated convex polytope. So if M is a collection of k element subsets of 1 through n, then we can let S sub m be the set of all points in the Grassmannian where your Pluker coordinate P sub I is non-zero if and only if I comes from your collection M. So, well, I should say S sub m may be empty, but if it's not empty, then this is called a matroid stratum. And then this gives us a stratification of the Grassmannian into these matroid strata. And they showed other things, like, for example, this matroid stratification is the simultaneous refinement of the n factorial Schubert decompositions that you get once you choose any total order on your standard basis. But unfortunately, the topology of these matroid strata is quite terrible. So shortly thereafter, Minyoff proved what's called the universality theorem, which has gotten cut off my slide. But the universality theorem says that the topology of the matroid stratum SM can be as bad as that of any algebraic variety. And okay, I'm saying it in a rather vague way, but this universality theorem wound up being a key tool in a subsequent paper of Ravi Vakil called Murphy's Law in Algebraic Geometry, Badly Behaved Moduli Spaces. Anyway, the point is these matroid strata have very bad topology. Okay. What's the debate? Okay, maybe I should take a pause for questions.
Perfect timing. So Greg Moore just asked, what's the definition of bad and terrible?
What's the difference between bad and terrible?
Sorry, what's the definition of bad and terrible?
Oh, just that, I guess I would rather deflect that. I would like to deflect the answer of exactly what that means to, for example, the Wikipedia entry on Minyoff's universality theorem. Basically, these can behave as badly as any algebraic variety, but you can look up the precise badness. Okay, so all right. So now you could ask the question, well, what happens if we take the previous story and we throw in the adjective positive everywhere? Now, the background here is that Lustig developed this theory of total positivity for partial flag varieties in 1994. So he introduced the totally positive and non-negative part of any real reductive group in such a way that the totally positive part of GLN recovers totally positive matrices. And he also defined the positive part of partial flag varieties. Constance Reach also made some key developments here in her thesis in 1997, giving cell decompositions of these things. But the reference that I'm really going to rely on here is Postnikov's 2006 preprint on the totally non-negative, which I'll sometimes call TNN, or informally positive Grassmannian. So, okay, so how is this defined? Well, we'll let the TNN Grassmannian, the totally non-negative Grassmannian, K-planes and n-space, be the subset of the real Grassmannian, where Plücker coordinates are simultaneously non-negative. Of course, everything, when we're talking about Plücker coordinates, they're coordinates in projective space. So I could equivalently say they're all of the same sign. All Plücker coordinates have the same sign. But I'll just say they're non-negative. Okay, so so this is a sort of, I don't know, maybe it's a strange sounding definition, but one can take this definition and try to do everything that was done before. So inspired by the matrix stratification, one can partition the TNN Grassmannian into pieces based on which Plücker coordinates are positive and which are 0. So again, let's let script M be a collection of K element subsets of 1 through n. And then we'll let SMTNN be the subset of the positive Grassmannian, where your Plücker coordinate P sub I of A is strictly positive if and only if I is in M. And otherwise, your Plücker coordinate must be 0, since we're requiring from the outset that all Plücker coordinates are non-negative. So now, in contrast to the terrible topology of the matroid strata, Postnikov showed that if this piece, SMTNN, is non-empty, then it's actually a cell. So it's called a positroid cell. It's homeomorphic to an open ball. And so we have this positroid cell decomposition of the non-negative Grassmannian. Okay, so just as a reminder, the matroid associated to a point in the Grassmannian is the collection of K element subsets of 1 through n, where your Plücker coordinate is non-zero. And then your matroid polytope, which I'll call gamma sub m, is the convex hull of the indicator vectors of all those elements I in your collection M. Now, if A belongs to the TNN Grassmannian, then we'll call M of A, so the matroid of A, a positroid, and we'll call gamma sub M a positroid polytope. And now one can look at, for example, what happens with the moment map. You can restrict your moment map from the Grassmannian to the TNN Grassmannian, and you still have the fact that every positroid polytope is the moment map image of a positroid cell, or separately, but also true, is the moment map image of a torus orbit of points in the TNN Grassmannian. And so GGMS gave this beautiful characterization of matroid polytopes by their edge directions. One can also characterize positroid polytopes, and these are precisely the matroid polytopes where facets have this very nice form, where this is I x sub I plus x sub I plus 1 plus x sub I plus 2 plus dot 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 up through x sub j equals some constant. Okay, so so when we throw the word positive into the whole story, then these very bad matroid strata restrict to positroid cells, and moreover, the cells can be completely classified, and they're naturally labeled by these beautiful combinatorial objects. So this was one of Postnikov's results. So I'm not going to give you the precise definition right here, but he showed that the cells of the TNN Grassmannian are in bijection with certain permutations called decorated permutations. And he also showed that the cells are in bijection with some equivalence classes of planar bicolored, this is planar bicolored, pronounced Plabic graphs. And these graphs also appear in the physics literature as on-shell graphs. Okay, so let me just explain briefly how you can read off positroid cells and positroids and the polytopes from these bicolored graphs. Okay, so I mentioned on the previous slide that positroid cells are in bijection with equivalence classes of some planar bicolored graphs. And specifically, these are graphs that are embedded in a disk, and there's boundary vertices labeled 1 through n, say in clockwise order, and internal vertices are colored black or white. So my two pictures here show examples of Plabic graphs. And I don't want to say too many details about this, but without loss of generality, we can assume our graphs are bipartite and that every boundary vertex is incident to a white vertex. So now how can we read off a positroid from this data? So we're going to look at perfect matchings of the graph. So let's let M of G be, so first we're going to look at all perfect matchings of our graphs G. And then for every perfect matching, so let me draw a perfect matching. So here is a perfect matching of my graph. And this perfect matching is incident to two boundary vertices. So if this red picture is M, if this matching is M, then I would say the boundary of M is 1 and 3. Okay, so I'm going to look at all the perfect matchings of my graph, and I'm just going to record the boundary vertices that they touch. And so let me just do one example. Let's call this graph G. Then I will have a perfect matching that uses edges 1 and 2. I will also have a perfect matching that uses edges 1 and 3. I will also have a perfect matching that uses edges, sorry, I should say, whose edges are incident to boundary vertices 1 and 4. I'll also have a perfect matching which uses boundary edges 2 and 3. I'll have a perfect matching which uses boundary edges 2 and 4. However, I will not have a perfect matching which uses boundary edges 3 and 4. So this is M of G for the graph G right here. And if this graph is G prime, well, it's a rotation of the other one. You can take graph G, cyclically shift the boundary vertices by 2, and we'll get M of G prime is 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. Okay, so that's how we associate collections of k-element subsets of 1 through n to such a graph. And the statement is that this M of G is a positroid. It is precisely the set of, it does precisely encode the non-zero Pluker coordinates of some point in the totally non-negative Grassmannian, and all positroids are obtained this way.
There was a question in the chat. Can you just say what's the definition of a perfect matching?
Oh, yes, sorry. So a perfect matching, perfect matching of a bipartite graph equals a, well, okay, I'll just say it in words. It's just a collection of edges of the graph such that every vertex is incident to precisely one of the chosen edges. So for example, this is a perfect matching. And let me also say, in the matchings that I'm looking at, I don't care about the boundary vertices, whether they're matched or not. We only care about that every internal vertex, every white and black vertex, is incident to precisely one edge from the matching. Other questions?
Not right now.
So you're not really using that it's bipartite, right? For the definition.
Oh, well, for the definition of what?
Of a perfect matching.
Right. I don't. Yeah. It's true. I don't have to use. Yeah. We could talk about matching of any graph. Yeah. Okay. So as I mentioned, these positroid cells, the positroids and positroid cells, are in bijection with equivalence classes of Playbit graphs, and so we saw how to read them off, and my picture's a little bit cut off, isn't it? You probably don't see the very bottom vertex of my octahedra, is that correct?
Yes.
That's right.
Does this help?
Yes.
Okay. All right. Excellent. Okay. Okay. So I think for this graph, G, we computed that M of G is 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, but we didn't have 3, 4 in the picture. And then we can associate the polytope to this data M of G. And what you get is the top half of this octahedron. And if you do the same game for this picture here, we get the bottom half of the octahedron. Okay, so that's just what our positroid polytopes look like for these small examples. Okay, so now let me switch gears and talk about the amplituhedron. So this was introduced by Arkani-Hamed and Trnka in 2013. And the amplituhedron is the image of the TNN Grassmannian under a particular map. So first of all, the amplituhedron depends on 3 parameters, n, k, and m. So let's fix n, k, and m, and we need that k plus m is at most n. And then we're going to choose Z to be an n by k plus m matrix where maximal minors are positive. So all the k plus m by k plus m submatrices of Z must have positive determinant. And then we define this map Z tilde from the TNN Grassmannian into the Grassmannian of k planes in k plus m space by sending our k by n matrix A to the just matrix product A times Z. And one has to check here that A times Z will have full rank and hence represents a element of the Grassmannian of k planes in k plus m space. Okay, so given that map Z tilde, we define the amplituhedron A sub nkm of Z to be the image under this map Z tilde of the TNN Grassmannian. So this is some subset of the Grassmannian of k planes in k plus m space. And of course, by its definition, the amplituhedron depends on Z, but its geometric and combinatoric properties appear not to. So I'm usually going to drop the Z. The amplituhedron has full dimension k times m inside the Grassmannian. And so why was it introduced? Well, in the case that m equals 4, its quote unquote volume is supposed to compute scattering amplitudes in n equals 4 super Yang mills. And for people who have thought about scattering amplitudes, the BCFW recurrence for computing scattering amplitudes can be at least conjecturally reformulated as giving a triangulation of the m equals 4 amplituhedron. So Yeah, okay, so this is the definition, a review again of the definition, and then I just want to explain a few special cases to help give a feel for it. So if M is equal to n minus k, then your matrix Z is going to be a square matrix. And so Z tilde is an isomorphism, and the amplituhedron just recovers the Tn and Grassmannian. If k is 1, the amplituhedron is going to be contained in the Grassmannian of one plane in 1 plus m space, so projective space. And in their original paper, Arkani-Hamed and Trnka showed that this is equivalent to a cyclic polytope with n vertices in projective space. And this is easy to see, so let me just kind of explain the m equals 2 example. So if we're talking about k equals 1 and m equals 2, then the map Z tilde is going to be a map from GR1n, non-negative, into the Grassmannian of one plane in 1 plus 2 space. And the way this map works is we're going to be taking our 1 by n matrix. So this 1 by n matrix represents a point in the Grassmannian. Fluker coordinates are non-negative, so the a sub i's are non-negative. And we're just going to map this to the matrix product by Z. And now Z is an n by 3 matrix. And the result lies in P2. And now let me just give names to the rows here. Let's just call the rows of this matrix Z1 through Zn. And now let's think about what happens if I map, if all of my a's are 0 except for a sub 1 equals 1, then this is just going to go under matrix multiplication to this row vector Z1 in P2. And similarly, E2 is going to go to the row vector Z2, E sub n is going to go to Zn. And the condition that maximal minors of Z are positive means that when I draw the Z sub i's in the projective plane, they're going to be in kind of convex position. So they're going to look like a convex polytope. And now, so the Z sub i's are the images of the E sub i's on the left-hand side. But now if I let, if I look at the image of an arbitrary point where the A sub i's are non-negative, then the image is going to land in the convex hull of this object. Okay, so that's why if k is 1 and m equals 2, we just get a convex n-gon. Okay, so, and more generally, we get cyclic polytopes when k is 1 and m is arbitrary. Okay, you can also look at the special case m equals 1. And with my former student, Stephen Karp, we showed that this is also very nice. We get the bounded complex of a cyclic hyperplane arrangement. And you can draw some pictures, and they look like this. Now, as I mentioned before, it's the m equals 4 amplituhedron that's supposed to encode geometry of tree-level scattering amplitudes. But let me also just say a few things about the m equals 2 amplituhedron. So this is considered a toy model for the m equals 4 case, and is itself supposed to have some physical meaning, which I don't want to say too much about since I'm not really an expert in that part of the story. Okay, so this is a summary of the special cases I've mentioned so far. But now what I want to illustrate is that this m equals 2 amplituhedron winds up being quite connected to the hypersimplex for some reason we don't entirely understand. Okay, so now I want to talk a little bit about triangulations of the amplituhedron. So the dimension of the amplituhedron is k times m, and this in general is less than the dimension of the domain of the amplituhedron map. Right, the amplituhedron is defined as the image of the TNN Grassmannian, and it's a kind of a projection onto a lower dimensional Grassmannian. So Z tilde is generally not injective. But now let's recall that we have this cell decomposition of the TNN Grassmannian into positroid cells. So now a natural question to ask is, can we find a collection of k times m dimensional cells of the TNN Grassmannian where Z tilde is injective, such that their images are disjoint and cover a dense subset of the amplituhedron? And if we can find something like this, then we call it a positroid triangulation. And I mean, yeah, the word triangulation maybe is misleading in that in general, these pieces are not going to look like simplices. But in this very special case where k is 1, then your pieces are simplices. Okay, so so why were physicists interested in understanding these triangulations? Well, it's because this BCFW recurrence for computing scattering amplitudes was conjecturally giving a triangulation of this amplituhedron. Rather, I guess I should say that Arkani-Hamed and Trnka, based on some prior work of Andrew Hodges, they were trying to find a kind of geometric basis for the BCFW recurrence. So the BCFW recurrence wound up being formulated, could be reformulated as some collection of cells in the positive Grassmannian, but those collection of cells looked sort of far apart. They didn't look like they had anything to do with each other. And so what Arkani-Hamed and Trnka were trying to do was find a geometric object, which was the image of the TNN Grassmannian, where the BCFW cells kind of fit together, decomposing one object. So that's what the amplituhedron does, conjecturally. Okay, but at any rate, I think the definition of triangulation is very natural, and some various special cases have been looked at, and so based on very special cases that had been studied, Stephen Karpin-Yang and I made a kind of crazy conjecture about positroid triangulations. So let's let M of A, B, C be this product. This is a famous number. It's the number of plane partitions contained in an A by B by C box. And this number appears all over mathematics. So what we conjectured is that the number of cells in a triangulation of the amplituhedron A sub n k m for even m is exactly the number of plane partitions that fit in a k by n minus k minus m by m over 2 box. And I guess I call it a wild conjecture because we have almost no evidence for it, but it's consistent with the results and conjectures for the m equals 2, m equals 4, and k equals 1 case. And it's kind of an intriguing conjecture because because this number m of a, b, c is symmetric in a, b, and c, it suggests symmetries among these parameters. Okay. But anyway, so in the m equals 2 case, this conjecture says that there's n minus 2 choose k cells in a triangulation of the m equals 2 amplituhedron. And this is the amplituhedron that I'm going to speak about the rest of this talk. Okay, so let's recall that when k is 1 and m is 2, the amplituhedron is extremely simple. It's just a polygon in projective space labeled by where the points correspond to the rows in our matrix Z. And you can work out this example in great detail. And the positroid triangulations of this amplituhedron wind up being precisely ordinary triangulations of the n-gon. So just things that look like this. And so each triangulation consists of n-2 triangles. And each of our triangles has dimension 2. And everything is known about triangulations of polygons. The total number of triangulations of a polygon, or equivalently, the amplituhedron A sub n12, is the Catalan number, which is given by this formula. And so this Catalan number will tell us that when n equals 2, we have 2 triangulations of our quadrilateral. Okay, so I'm going to come back to this number 2 and the number Catalan. Okay, so we've talked about 2 maps from the positive Grassmannian. One of them is the amplituhedron map, and one of them is the moment map. So in analogy with the triangulations of the amplituhedron, we can define positroid triangulations of the hypersimplex. These are also called fine positroidal subdivisions. So this is a review of what the moment map looks like. And now let's define positroid triangulations, just in analogy to what we did for the amplituhedron, but now we'll do it for the hypersimplex. So the moment map is a map from the TNN Grassmannian to Rn, and the dimension of the image, well, okay, so the image of the TNN Grassmannian is the hypersimplex, and this has dimension n-1 because it lies in the plane cut out by the fact that the sum of the coordinates is always k. And so we'll define a positroid triangulation of the hypersimplex to be a collection of n-1 dimensional cells of the TNN Grassmannian, where the moment map is injective, and we will also want their images to be disjoint and cover the hypersimplex. And when I say cover, I mean cover a dense subset of it, or equivalently, we can take the closures of the images, and we want those to cover the hypersimplex. Any questions?
There was one question, it may be more a question for a physicist, but I'll just try it out. Is there a physical significance of the fact that the amplituhedron is homeomorphic to a ball?
Oh, I don't know if there's a physical significance. Yeah, but yeah, we could throw that out at the end and maybe a physicist can answer. Okay, so so now let's talk about positroid triangulations of delta 2n. So this is the hypersimplex for which is the moment map image of Grassmannian of 2 planes in n space. And here, positroid triangulations consist of n-2 positroid cells, each of full dimension n-1. And one can show that the total number of positroid triangulations is the Catalan number. So that's a special case of something we proved with David Speyer. So we can look at our example of GR24. And here there are 2 positroid triangulations of the hypersimplex GR, which of this of the hypersimplex delta 24. So I can either split the hypersimplex in 2 along this square, and then the top and the bottom are both positroid polytopes, which are injective images of positroid cells in the non-negative part of GR24. Or I can split it in 2 along this square, and this is also then both sides, so both pyramids on either side are also injective images of cells in GR24. So there's another way, I should say, of splitting this octahedron in half, right? I could take this red plane and rotate it 90 degrees, and that would give another way that combinatorially looks like it's doing the same thing. It's splitting it, my octahedron, into two pyramids, but that's not a positroidal subdivision. Okay, so so there's two of these positroidal triangulations of delta 2, 4, and and the claim is that this number 2 corresponds to the 2 that we saw before when we were studying the amplituhedron. So for A sub 4, 1, 2, I get a foregone, and my claim is that these two positroidal subdivisions here exactly correspond to the two triangulations of a foregone. Okay, so just as a recap, we have two maps on the TNN Grassmannian. We have our amplituhedron map, and we have our moment map. And we have two notions of positroid triangulation. If we're talking about positroid triangulations for the amplituhedron, A sub n k2, then our triangulation is given by a collection of two k-dimensional cells of the TNN Grassmannian, where z tilde is injective, such that images are disjoint and cover the amplituhedron. Now, if we're talking about the hypersimplex delta k plus 1 comma n, then our notion of triangulation means a collection of n-1 dimensional positroid cells, where the moment map is injective, such that images are disjoint and cover this hypersimplex. And for k equals 1, we got Catalan many triangulations for both of these situations. And so apparently positroid triangulations of the amplituhedron, at least numerically, are in bijection with positroid triangulations of the hypersimplex. And the claim is that this holds for general K. Now, before I can talk about this claim in more detail, I just need to say a little bit more about the combinatorics of positroid cells. So I mentioned that Postnikov classified cells of the TNN Grassmannian, and he showed they were in bijection with certain permutations. So, okay, a decorated permutation is just a permutation in which every fixed point is either designated loop or co-loop. I mean, you could call them black or white if you like. For metroidal reasons, we call them loop and co-loop. And then, moreover, cells S pi of the TNN Grassmannian are in bijection with decorated permutations pi on the set 1 through n with k anti-exceedances. And you don't really need to know this definition, anti-exceedance, but just for completeness, it's a position I where pi of I is less than I, or pi of I is a fixed point, which is a co-loop. And these decorated permutations are very nice. You can read off the description of your cell from pi. And you can also, there's also an easy correspondence between the decorated permutations and these planar bicolored graphs that I talked about earlier. So given a, okay, for technical reasons, I need to say reduced, given a Playbit graph representing a positroid cell, you can read off the permutation pi by following the rules of the road. In some literature, this is also called zigzag paths. So we're going, okay, so let me explain how to associate a permutation to these graphs. So I'm going to start at every boundary vertex, 1 through n in turn, and I'm going to go out on my first edge, and whenever I see a black vertex, I'll turn right, and whenever I see a white vertex, I'll turn left. So if I do this for this graph here, I start at 1, I go out, I turn left, which just means going straight, then I turn right, and then I turn left, and I get to 3. And then if I do this starting from 2, I walk through here, I turn right, and I go to 1. Now, if I start at 3, I'll go out this edge, and then I turn left, and I get to 4. And if I start at 4, I'll go out, I'll turn left, turn right, and I get to 2. So this is the permutation associated to this graph. And similarly for the other graph, if I start at 1, I'll walk out here, I'll turn left, I get to 2. If I start at 2, I turn left, right, left to 4. If I start at 3, right, left to 1. And if I start at 4, I turn right and I get to 3. Okay, so anyway, the upshot is that these cells are naturally labeled both by equivalence classes of these Playbit graphs and also are labeled by these decorated permutations. And you can go back and forth between the descriptions very easily. Okay, so, so now our conjecture with Lukowski and Parisi is that positroid triangulations of the amplituhedron, so for m equals 2, are in bijection with positroid triangulations of the hypersimplex delta k plus 1 comma n. And I'm going to describe that bijection in a moment. But I'll just remind you that triangulations of the hypersimplex consist of n-1 dimensional cells of the Grassmannian of k plus 1 planes in n space, while triangulations of the m equals 2 amplituhedron consist of 2k dimensional cells of a different Grassmannian. So we have to map n-1 dimensional cells of grk plus 1 comma n to 2k dimensional cells of grk comma n. And we have a nice labeling of our cells by certain permutations. Okay, so how are we going to make this bijection? So, so it's a very, very simple map, in fact. So given a loopless, okay, it just means no fixed point is a loop. So given such a permutation pi, which I'm writing as a list of numbers a1 through a sub n on 1 through n, we'll define pi hat by just doing a cyclic rotation of the labels. And then in pi hat, I'll just say that any fixed point is called a loop. So we call this the T duality map by analogy with a map that's been made for m equals 4. And the first lemma is that this T duality map, which maps the cell labeled by permutation pi to the cell labeled by permutation pi hat, is a bijection between loopless cells of this Grassmannian and co-loopless cells of this Grassmannian. And moreover, it does something very predictable to the dimensions of the cells. In particular, it maps n-1 dimensional cells over here to 2k dimensional cells here. Okay, and this map we're writing down is an m equals 2 analog of a map that was used by Arkani-Hamed, Bourgelat, Kachazo, Gontroff, Postnikov, and Trnka in a paper they wrote a few years ago to relate twistor space to momentum twistor space. Okay, so this is the map. And the conjecture is that a collection S pi of cells of the TNN Grassmannian gives a triangulation of the hypersimplex if and only if the corresponding collection of cells of this other Grassmannian gives a triangulation of the amplituhedron. So this is a picture of the two positroidal subdivisions of delta to 4 that I showed before. And on each side of the picture, I have a way of splitting this octahedron in two, and the two pyramids are labeled by these planar bicolored graphs, or equivalently by permutations. And on the other hand, our amplituhedron here corresponds to a foregone. And again, we have two triangulations of the amplituhedron, and I've labeled the triangles by Playbit graphs and equivalently by permutations. And you can see that if we apply this kind of T duality map to the permutation, which just does a cyclic permutation of indices, then this permutation goes here, and this permutation maps here. And similarly, this permutation maps here, and this permutation maps here. Okay, so in this very small example, it appears our conjecture is correct. Now we can prove the conjecture is true for quite a lot of triangulations, in fact. So, so we gave this kind of graphical recursion, which constructs triangulations of the hypersimplex in terms of triangulations of smaller hypersimplices. So what do I mean by this picture? So this is supposed to be a picture for, this picture is having to do with Playbit graphs. So Playbit graphs, remember, correspond to cells, so correspond to pieces in our triangulation. And so what this picture is saying, I'm afraid the font might be a little small, but what it's saying is that if over here, I have a collection of Playbit graphs giving a triangulation of the hypersimplex delta k plus 1 comma n minus 1. And if I take each one of those graphs in turn, and I kind of augment those graphs to this picture here, adding this white vertex. And if separately, I take an arbitrary collection of Playbit graphs giving a triangulation of this hypersimplex, and I in turn augment each of those graphs as so, then this big collection of Playbit graphs that I have will give a triangulation of this hypersimplex. Okay, so this is a recursion that gives us many triangulations of the hypersimplex. And then separately, a theorem of Bao and Xu gave a graphical recursion constructing triangulations of the m equals 2 amplituhedron. And it looks like this. And one can check that these recursions are precisely in bijection via this T-duality map that I described before. So anyway, so the conjecture is true for sort of infinitely many triangulations, though we don't know if it's true for all of them. Okay, maybe I should pause for questions.
There's one question. Isn't T-duality, is that meant to be related to the way physicists use the word T-duality?
Yes, and okay, so I'm not an expert in this, but it's related to the fact that there's two formulations of scattering amplitudes in n equals 4 super Yang mills. One's in momentum space, one's in momentum twister space. And this apparently came from an amplitude Wilson loop duality, which in turn came from this duality in string theory called T-duality, I think work of Berkovitz and Maldacena. So I think my answer is yes. Okay. Okay. So let's see. How much time do I have left?
We started a few minutes late, so maybe 7 minutes or so.
Okay. So I just wanted to say a little bit about how we guessed that there was a connection between these two objects. And in a nutshell, it came from studying good triangulations of the amplituhedron and noticing a kind of a numerology connection to the positive tropical Grassmannian. And so this was our definition of triangulation. But many of the triangulations of the amplituhedron are bad in the sense that boundaries of images of cells overlap badly. And you can make a definition of good triangulation where what we would like to happen is that whenever the images of two cells in our triangulation, whenever they overlap in codimension 1, we want this overlap to itself be the image of a cell in the closure of both of the cells we started with. So you want things to interact nicely at the boundary. And so one can compute the number of good triangulations of the amplituhedron. And for a sub n1, 2, you get the Catalan number. And if you then look at a sub n2, 2, you get 1, 5, 48, 693 for the first terms in your sequence. Okay, now Matteo and Tomek came to me with these numbers, and I recognized the numbers from a 2005 paper that I wrote with David Speyer, where we studied the positive tropical Grassmannian. So this is a polyhedral fan, and the number of maximal cones in trop plus GR2n is the Catalan number, and the number of maximal cones for the Grassmannian of 3 planes in n space starts out as 1, 5, 48, 693. And so it was very striking that we were recreating precisely the same sequences here. Just to make a small remark that the positive tropical Grassmannian is connected to the cluster structure in the Grassmannian. Okay, so it was trying to figure out this connection that was the starting point for our work. let's see. So I think I'm going to kind of just be vague about what the positive tropical Grassmannian is. The vague way to say it is that you can define varieties over the field of Puiseux series, and then look at your variety and take a valuation map that gives you this piecewise linear analog of your variety. And so anyway, so you can make this definition of the positive tropical Grassmannian. I'm skipping ahead because there's a very simple way to define the positive tropical Grassmannian. It's a region in space just cut out by some inequalities. So what are these inequalities? So, okay, so let's P be a point in R to the n choose k. So it's just a vector in R to the n choose k. And I'm going to say that P is a positive tropical Plucker vector if for any A, B, C, and D, and S, the k minus 2 element subset disjoint from the others, I have either this inequality or this inequality. And if you're familiar with the three-term Plucker relations for the Grassmannian, then these should look like kind of piecewise linear tropical analogs of the three-term Plucker relations. So this is not how the positive tropical Grassmannian was originally defined, but one can show that the positive tropical Grassmannian is exactly the set of positive tropical Plucker vectors. So the point is, it's simply a subset of R to the n choose k, where a whole bunch of inequalities hold. And it has a fan structure that's given by these inequalities, whether or not they achieve equality or are strict. Okay, so now we have our amplituhedron map and our amplituhedron, and then we have this positive tropical Grassmannian, which is the set of positive tropical Plucker vectors. And so what we were observing was that good triangulations of the amplituhedron seemed to be in bijection with maximal cones of the positive tropical Grassmannian. So why was that? We wanted to relate the positive tropical Grassmannian to some kind of triangulation or subdivision. And our inspiration here was some old work of Speyer related to older work of Kaprenov, relating tropical Plucker vectors to matroidal subdivisions of the hypersimplex. Okay, so I'll just explain how this works for the positive Grassmannian. Okay, so if you want to construct a subdivision of a polytope in general, and the hypersimplex in particular, one very nice way to do it is to choose a vector P in R to the n choose k. And now we're going to think of this vector P as giving us a height function on the vertices of our hypersimplex. So let me think of each real number P sub I as a height, a new height that I'm going to lift vertex E sub I to. So I'm basically going to put delta Kn in a space of dimension 1 higher by lifting up every vertex to a height given by this vector. So you can take the convex hull of this bigger polytope and project its lower faces back down to the hypersimplex, and you get what's called a regular subdivision of the hypersimplex. So something we proved is that if P is a vector in R to the n choose k, then the following statements are equivalent. The first statement is that P is a positive tropical Plucker vector. In other words, it satisfies these inequalities that are analogs of three-term Plucker relations. And the second statement is that in our corresponding subdivision of the hypersimplex, every face of that subdivision is actually a positroid polytope. So the point is that points in the positive tropical Grassmannian give rise to decompositions of the hypersimplex into positroid polytopes. And this is a positive analog of a result of Speyer. And it was also anticipated or known by various other people and also appeared independently in work of Arkani-Hamed, and Trnka. Okay, but the upshot is that regular positroids triangulations of the hypersimplex correspond to the maximal cones of the positive tropical Grassmannian. So we started out by wanting to relate the positive tropical Grassmannian to subdivisions of the amplituhedron, and a first step along the way was relating them to subdivisions of the hypersimplex. Okay, so so I'll just now summarize the whole picture. So on the one hand, we have this classical object, which is the moment map. Oops. And this is a map. Well, it was originally defined for the Grassmannian, well, actually defined more generally, but the moment map in particular can be thought of as a map from the TNN Grassmannian to the hypersimplex. And on the other hand, we have the amplituhedron map, which is also a map from the TNN Grassmannian, whose image is the amplituhedron. And on the moment map side, one can talk about positroid triangulations of the image. And our triangulations consist of n-2 choose k, n-1 dimensional cells of this Grassmannian. And then on the amplituhedron side of things, we can talk about positroid triangulations, and triangulations consist of n-2 choose k, 2k dimensional cells of this Grassmannian. And the conjecture, which is true in infinitely many cases, but open in general, is that this simple T-duality map, which takes cells indexed by permutations pi up here to cells indexed by permutations pi hat down here, gives exactly this correspondence between the triangulations. Anyway, this sort of begs a lot of questions, but one of them is why is it that the moment map is related to the amplituhedron map? At least on the surface, the maps look completely different. And how can we use the relation to better understand the amplituhedron? So I will stop there.
Thank you very much. Let's thank the speaker. All right, so now it's time for questions. So if anyone has a question, just raise your hand. Use the Zoom raise hand thing, which should be at the bottom of the participants panel. And then I can call on you and you can unmute yourself. We already had, of course. All right, and maybe I can lead off a bit. So if I understood right, you said that, so the moment map that you have on the top of your picture here is like a totally canonical thing. And the amplituhedron map, on the other hand, depends on the choice of this Z.
Right.
And you said that you said something like, well, the image is in some sense independent of Z. Can you say that more sharply about that?
So, I mean, I guess it's sort of all conjectural. But for example, any combinatorial property that you might ask of the amplituhedron for one Z should be the same if you change Z. So for example, whether or not a collection of cells of the positive Grassmannian, whether or not it gives a triangulation of the amplituhedron should be totally independent of your choice of Z.
I see, but you're saying generally nothing like that is proved.
Right. Yeah. There's sort of a shocking amount that's not actually on solid footing. Yeah.
Got it.
Yeah. And I mean, one of the main things that would be nice to really understand is, I mean, it would be nice to give actually a proof that these BCFW cells actually give a triangulation of the amplituhedron. So there was this original motivation that led Arkani-Hamed and Trnka to define the amplituhedron, because there was this sort of well-defined notion of BCFW cells, which were 4K dimensional cells in the positive Grassmannian, and they were encoding scattering amplitudes. And conjecturally, the images of those cells give an honest triangulation of the amplituhedron, but that hasn't actually been proved.
Got it. Thanks. Another thing I was wondering about, since you mentioned, at some point you mentioned cluster structures, is there, this is probably a lot to hope for, but is there any known analog of this duality that you summarized on your last slide? Is there any known analog of that for any other cluster algebras?
Oh, you mean this duality here? Or
I guess that would be prerequisite for the thing on the right, yeah.
Sorry, I'm not sure if I completely understand your question.
Well, the question is a little bit ill-posed. So I was just imagining, you know, if I have some other kind of cluster variety that has a torus acting on it, then I could study the moment map, and I could ask, you know, whether some kind of triangulations of its image correspond to something else.
Oh, right. Yeah. Right. Yeah, that's a good question. I'm not aware of anything like that, but I mean, one could, I suppose the first thing one could try to do is look at Grassmannians and flag varieties of other types and hope you could do something like that there.
I received a message from Nima Arkani-Hamed saying he can make a comment. Yes, please make your comment, Nima. Let me unmute you. If I can you raise your hand, Nima? Never mind, I found you.
Okay, guys, just quickly, maybe Lauren, you said this, but first, just on the issue of what depends on Z, the claim is that the shape of the amplituhedron, its facet structure, does not depend on the Zs so long as the Zs are positive. So they do have to be a positive. That they have the external data has got to be positive in the sense of the positive Grassmannian. And the kind of mental image is if you just plonk down a bunch of points on the plane and you ask for their convex hull, obviously what you'll get will depend on exactly where they are, except if you say that the points are convexly ordered. So if you say ahead of time that if you restrict the minders of all the 3x3 matrices that you would make with the external data represented projectively as 3 vectors, if you just say that all the ordered minders are positive, that forces the polygon to always look convex. And so the shape doesn't actually depend on precisely what they are, so long as it's convex. I think there was also a question that came up earlier, whether there's any physical significance to the amplituhedron being a ball. I certainly don't know of any physical significance of it, but I can just say it's just a miraculous fact that played a very important role in discovering these things to begin with. Long before we knew there was any geometry, we could look to see whether there's any hope of some kind of geometry, because simply from the rational forms that we get from the integrand of the amplitude, we can get an idea of what we might mean, what we might think the facets are, just by taking residues of these forms and sort of using them to define what we might mean by the notion of facet. Just looking at what all the independent algebraic, all the independent rational objects that we get in this way. If you do that, you can just count how many you would have in every dimension, and the number quickly grows into the millions, you know, even for like 7 to 8 external particles. And then you do Euler sums of these numbers of order millions everywhere, and miraculously they all cancel out and you get 0 in the end. So that's some indication that there's a geometry controlling all of them. But why that geometry exists is not obvious. I mean, so why the amplituhedron exists is not obvious. They're all sort of related to each other.
Great, thanks. I think we have a question also from Albert Schwartz. Go ahead.
Is the limit of quantum Grassmannian. And I wonder if there are some statements that involve quantum Grassmannian.
Albert, can you improve your voice, your sound?
Sorry? Hello? Do you hear me?
We can hear you, but the volume is very low. Is there a way you can increase the volume?
Or possibly type in the chat, if that's easier.
Is the limit of quantum Grassmannian. Is it correct?
For me, at least, it's still very difficult to hear.
Sorry, I can't go.
Yeah, maybe, would you be able to type your question?
Yeah. Sorry. Yeah. I can't. I will send the question to Laura.
Oh, did you say you've sent the question privately to Lauren?
Yes.
I didn't see
I see.
it.
So Lauren, it should be in your chat window.
Oh, maybe it's the other Lauren. I do not see it in my chat.
Albert, could you send it again, but just send it to everyone?
I see a question of Lisa Jeffrey that I can answer quickly.
Oh, yes, I didn't see.
Question was that the T-duality map is bijective. So you said the T-duality map is bijective in infinitely many cases. Are there any cases known where this map is not known to be bijective? So we believe it's a bijection. It's just that we can't prove that in complete generality, but we're not aware of any. As far as I know, there's no counterexamples. I'm completely sure it's correct, but we just don't have a proof in full generality.
We also have a question from Atul Sharma.
Yeah. So does this T-duality map extend to the loop amplituhedron as well?
Oh, so I don't know.
Actually, I don't remember whether there was a notion of loop amplituhedron for m equals 2, but if there was.
Yeah, I'm also not sure about that, but Nima could presumably tell us.
Yeah, there isn't really there isn't at least a totally canonical notion of a loop amplituhedron for m equals 2. There is something that you can define for m equals 2, but the loops would need an ordering, which we don't have for m equals 4. In fact, I mean, for anything that for m is 0 mod 4. You can come up with some interesting generalizations of what you mean by loops, but for literally m equals 2, the sort of problem would be that the loops would have to be associated with points, and so then you need to give some extra notion of how the loops are ordered relative to each other to sort of define all these things. So we don't actually have a decent notion of a loop amplituhedron for m equals 2.
Right.
But there is for m equals 4. I mean, there is for m equals 4, obviously, m equals 8, and so on. There is some these objects for higher m generalize sort of field theory amplitudes in interesting ways. Instead of giving you sort of field theoretic objects that factorize in 2 on their singularities, they factorize in 3, 4 higher components. And the notion of what loop corrections are also has a more abstract generalization, but only for m equals 0 mod 4.
Right. So if there is a hope to extend this T-duality map to m equals 4, then we might have to think of loops as well. That's why I was asking.
Well, I mean, it does exist for m equals 4. I mean, what you would need is, but I mean, it exists. Yeah, it doesn't quite exist, but what would make it? But it should exist because it's just the amplitude Wilson loop duality. The amplitude Wilson loop duality, that fermionic T duality, as Lauren was correctly referring to it, that's the origin of the Yangian symmetry, blah blah blah, so that we know exists. The connection to the amplituhedron, the Grassmannian, sort of trivializes it to some extent. I mean, makes it obvious why such a duality exists, which isn't obvious from the field theory side. But to see it fully at the level of the geometry at loop level, you would need a loop amplituhedron in momentum space instead of in momentum twistor space, and that's something that surely exists but has not quite been defined yet.
Right. Thanks.
Actually, while I'm on here, instead of typing, I have a question for Lauren instead of a comment. Can I just ask, Andy? Okay.
Go ahead.
So, Lauren, so you've given this this beautiful association between vertices of the tropical Grassmannian polytope and triangulations of the hypersimplex, right? That's one way of talking about it. Do you have any hypersimplicial interpretation of what the facet structure of the tropical Grassmannian polytope is?
Oh, yes. So yeah, I only talked about these fine subdivisions for simplicity, but we could talk about any subdivisions. So in particular, we can drop the word. So when I define triangulation, I asked that the Z tilde map be injective, but we can drop that assumption. And then the different faces, the different cones of all
just correspond to different to the coarser ways of dividing the hypersimplex.
Right. Or
but I meant that there's some very interesting structure that I at least don't understand. For example, for m equals 2 for the isosahedron, every way, everything just begins by slicing the hypersimplex in 2, or all the boundaries of the G2n tropical Grassmannian, that's just the isosahedron in that case, correspond to factorization, correspond to direct products of lower isosahedra. But we know that for higher K, much more interesting things happen. Again, they sort of break up into 3, 4 higher pieces, and there's all sorts of sort of rich geometry in what the boundary structure of that tropical Grassmannian looks like. And
so you mean like the different kinds of coarse subdivisions, like 3 splits or 4 splits and so on?
Exactly. Yes, exactly. Yeah. Is there some, I'm asking whether there is some sort of natural combinatorial or any other understanding for what all the different kinds of split of the hypersimplex look like, sort of a priori ahead of time.
Yeah, it's a good question. We've looked at that a bit. We don't feel like we have a complete understanding of that. Yeah. So anyway, I don't have a good understanding right now, but it looks really interesting.
Thank you.
Oh, Albert Schwartz wrote the question. He understands the tropical Grassmannian as a limit of quantum Grassmannians. Can one reformulate some of your statements in terms of quantum Grassmannian, as in my paper with Movshev? Yeah, I guess I don't have a good answer to that question. I haven't really thought about the tropical Grassmannian as a limit of quantum Grassmannians. Yeah, I don't know. That sounds really interesting, but I don't have anything to say about that question right now.
All right. If there are no further questions, let's thank the speaker again.
Thank you.
Thanks very much for coming. Thanks for this marvelous talk. And so that brings this week's colloquium to a close. We are now back on a 2-week schedule. So the next colloquium will be 2 weeks from today, October 5th, and the speaker is Natalie Paquette. So hope to see you there.
Okay. All right. Thanks so much, Andy.
Thank you.
Oh, is there a way for me to save the chat? Is that something that?
Oh,
I think it's saved automatically.